Hello everybody, we will be talking about section 7.5 today, dealing with integration strategy. Now integration strategy is basically, we get a problem, how are we going to attack it? Now the first step in it is to simplify. A lot of times we'll get something unnecessarily complicated on a test, or we plug something into a formula, and that formula gets something, that's complicated. So what we're going to do is we're going to use our trig identities, simplify as much as we can, or into a form that we can apply one of our later methods to. We can cancel variables out. We can split the fractions like so. Now this is a really simple example, but we can use it to do things to make it in a form that we can apply, say, one of our later methods on. Now, failing that, we have simple substitution. Sometimes we'll get caught up into thinking, oh, this is a really hard final. We're gonna need everything's gonna be complicated, but in reality, it's just gonna be it can be solved by simple use substitution. So always try that first. And now that we've established that all these simple methods have failed, we're going to have to get to our advanced BC strategies, the one we've learned in BC. We have things like, if it's a rational expression, polynomial over polynomial, we're going to use our partial fraction decomposition learned in 7.4. If it's a trig function, a log, or e to a something with x to a something, we're going to use our integration by parts, or something that's, it doesn't have to be x or something, it has to be something that will go away after you derive it a few times. Now, if it's a trig function, we're going to use our trig integrals that we learned in 7.2, along with our, power reduction and double angle formulas and half angle. If it's in the root, in this form, you're going to use one of our trig substitutions that we learned in 7.3. And again, we can also, at this point, we want to rework it again, use some of the earlier strategies, after we tried, we know maybe we can go another direction. We can also do completing the square, and then we can also rearrange the trig functions to be more aligned with one of these methods. And again, we can also relate it to something we've learned in the past. If we something that's really similar to it, we can see, relate them to each other. And again, a lot of these will be multi-step problems. So it might not just be applying integration by parts or partial fraction decomposition. You might need to apply multiples or something really easy that I talked about in the first step, and one of these or something like that. And if all else fails, try again. But if it's during a test, don't try too many times. Go on. Maybe you'll find some insight on later problems. So this is our first example problem: integral of e to the negative 2t cosine t dt. So since this is a repeating function, something that cycles through, cosine t times another thing, we will use integrating by parts. Even though this does not go away neatly after we take the derivative a few times, we're still going to use it as a u, and dv has to be cosine of t. Now, a common mistake here would be to integrate or derive mistakenly and get a bad du or v value, so be sure to double check your work. Now, once we integrate by parts, this is our result. Now we see this integral, it's not very clean. It's still something that is a candidate for integration by parts. So we'll do that again. And this is what we get. And notice here, since that cosine has cycled from cosine to sine to cosine again, this is just negative 4 times what we want. So since this is equal to this, we can move this over to here. So 5 times integral of e to the negative 2t times cosine t dt equals e to the negative 2t times sine t minus 2e to the negative 2t times cosine of t. Divide both sides by 5, and the integral of e to the negative 2t cosine t times dt, which is what we want in the first place, equals e to the negative 2t times sine t minus 2e to the negative 2t times cosine t all over 5 plus c. So this is our second example problem. Integral of 3x squared minus 17x squared plus 36x minus 35 all over x squared minus 4x plus 4. Now, since this is a polynomial over a polynomial, it is most likely a good candidate for partial fractional decomposition. But before we can do that, we have to divide it, do some algebraic manipulation. And after we divide it, we get 3x plus 5 plus 4x minus 15 over x minus 2 squared. Now we're going to decompose this part. So the format for that is a over one factor to the denominator plus b over the other factor denominator, and if there was more factors denominator, we would do c, d, e, etc. Now after we put it into this form and set it equal to the numerator, we get a equals 4 and b equals -7. Now here a lot of people might, just integrate this part and completely forget about 3x plus 5. I've done it myself, so do not forget about this because it is still part of it. Now after we bring these two elements together, we get integral of 3x minus 5 plus 4 over x minus 2 minus 7 over x minus 2 squared dx. Now using our standard integration tactics, we have 3/2 x squared minus 5x plus 4 ln of absolute value of x minus 2 plus 7 over x minus 2. This is going to be our third example problem, integral of root 9 minus 4x squared dx. Now for this one is in the general form a squared minus x squared, so we're going to use trig substitutions for this one. Now before we do that, we're going to have to work with it a little bit and simplify it a little bit into this form, which we can trig sub with sine equals 2/3 x and cosine t dt equals 2/3 dx. Now a common mistake is that people would forget to do this, so this is very important. Do not forget to do that. So here we have this, we have brought down here, and after we plug in the trig substitutions, we have this right here, and using our trig identities, it becomes 9/2 integral of root cosine squared t cosine t dt, which is just 9/2 integral of cosine squared t dt, which after we use some more trig identities, we make it into this, which we integrate into this using our integrals. Now after we've done that, we can use some more trig identities, the half angle formula, which is sine t equals 2 sine t cosine t, and put into this form. Then since sine t equals 2/3 x, we do some trigonometric manipulation, which means t equals arc sine 2/3 x, and we also need to find cosine t. So using this again, which we established in the beginning, we put it into a right triangle and use the Pythagorean theorem to complete the right triangle. And so cosine t equals root 1 minus 4/9 x squared. And to put this back and leaving it as t and not as the x as originally asked for, that's also a common mistake, so be sure to avoid that on an exam. So our final answer is 9/4 arc sine 2x over 3 plus 1/2 x root 9 minus 4x squared plus c. And again, do not forget the plus c because it's an indefinite integral.